Hello everyone. Welcome to the TCS seminar at Jagiellonian. Today our guest is Małgorzata Sulkowska. She did her PhD on optimal stopping problems, and then she started work on graph theory and on complex networks. She spent 2 years in INRIA Sophie Antipoli. Now she is at Wrocław University of Science and Technology, and the title of the talk is The Modularity of Minor Tree Graphs.
Thank you. Thank you very much for introduction, and thank you very much for invitation. So today's talk is going to be a graph parameter called modularity, and this is a parameter which is quite important in the area of complex networks. And in this area, complex networks refers to graphs that can mimic well the structures of real life systems, like some social networks, technological networks, maybe biological ones. And one of the main points of interest in the area of complex networks is to discover, to understand, and to describe the structure of the graph. And modularity is the parameter which gives some insight into the community structure of the graph. And a little bit more, speaking in a little bit more details, it measures the presence of community structure in the graph. So whenever we deal with a graph which is such that the set of its vertices can be divided into the subgraphs, into the subsets, such that the subsets are like densely connected, but there are not too many edges in between the groups, then we will expect this graph to have high modularity. And otherwise, if the structure is rather chaotic, if there are no so tightly, densely connected regions, we'll expect, or we would like this graph to have low modularity. And the modularity has got a number of applications. So it is widely used in graph clustering algorithms, in algorithms for community detection. For example, in social networks, one would like to identify such densely connected communities in order to identify the groups with similar interests. If you would like to target some information better, then you can use it. In biological networks, it identifies, for example, the proteins such that they have similar functionality in biological cells. And it's also very useful just by visualization of the graphs. And it's really like from practical point of view, it's really already like widespread and well established. And all right, so today's talk, at the beginning, I'm going to give you the rigid formal definition of modularity, and I'm going to spend some time on it. And I'd like to also to give you some intuitions and its behaviors, which are some, well, intuitive, some are counterintuitive. Later, I will introduce the notion of the maximally modular class of graphs. And later, I'll state the problem about this maximally modular class of graphs, and I'll try to sketch the solution. So, all right, so let's start with the definition. And before one defines modularity, one has to define the modularity score of the partition. All the graphs will be undirected. All the graphs are going to be simple. And I assume that the graph always has at least one edge. So for a given graph and for a given partition of its vertices into induced subgraphs, which I will also call communities or clusters throughout the presentation, the modularity score of the partition is given by this formula. All right, so by E of A, I understand the set of edges that are all contained in A. By E of G, the set of edges of the graph. By deg of A, I understand the sum of degrees of the vertices that are contained in A. And if deg does not have any subscripts, I refer to the degree of V in the whole graph G. So, all right, so this is the formula. Let's just check two small examples. So the first one, we are given the graph on 7 edges, some partition called here A. And this is quite a, let's say, convenient partition. We have a click in the first set, almost click in the second set, only two crossing edges. And the formula for modularity goes like this, that we have 3 edges in the first community, out of 7 in total, 2 edges in the, it's not easy from this angle, 2 edges in the second community out of 7 in total. The sum of degrees in the first community is 3 plus 2 plus 3, which gives this 8 over the total sum of degrees in the whole graph. And the same for the second part. And we arrived at the modularity score equal to 10 over 49. Let's check what changes if we change the partition. So let's take the same graph, just we change the partition. So right now, the partition is a little bit more, let's say, chaotic. There are 4 crossing edges. We are left only with 2 edges in each part. So here we have 2 over 7, and 1 edge in the second part, and 1 over 7 over there. And this is just the coincidence that the sum of degrees in both parts didn't change, again, 8 and 6. But altogether, the modularity score of the partition dropped, and it even dropped below 0. All right. So this is just the formula, and the first part of the formula can be, of course, easily interpreted, as over here we look into the fraction of edges that fall into communities in total. But how about the second part? So where does actually this squared quotient comes from? And the modularity is actually the comparison of the graph we are working with together with some random multigraph. So so this second part of the formula comes from the fact how is it calculated? So we have a graph G that we are working on, and we consider a graph on the same set of vertices, preserving the same degree sequence. We look into the same partition, just we consider that the edges over here are wired randomly. So we get some random multigraph. Now we can have multiple edges, we can have loops. And instead of literally the number of edges in part A, over here we look at the expected number of edges that falls into community A if we consider this random graph. And if we do some simple calculations, we arrive at this squared quotient. So this is where the second part of the formula comes from. So actually modularity is a kind of a comparison between the real life graph we are working on and a random graph which preserves the same degree sequence. That's the philosophy behind this formula. All right, this first part is very often called edge contribution, and the second one is very often called degree tax. And it's quite easy to show that the modularity score of the partition always falls into this interval. So upper bound is very easy, as you can easily observe that the edge contribution is at most 1, and the degree tax will be always greater than 0 because I assume that we always have at least 1 edge. The lower bound is not that trivial, but it's also not very difficult. You just have to come up with some graph and propose like a partition which is exactly not capturing the densely connected communities. I can leave it as a small riddle. All right, so this was modularity score of the partition. So I guess that it's gonna be pretty easy to guess how modularity is defined. And modularity of the graph is just the maximum of the modularity scores of the partition over all possible partitions of the graph, right? The modularity already always falls into the interval 0, 1. Upper bound again is trivial, as always modularity score was less than 1. And how about this 0? So there exists some obvious trivial partition that will give modularity score equal to 0 for each graph. And it is just the partition which has a single set, and it is just the set of all vertices. If you consider such a partition, edge contribution is 1, all the edges fall into this one community, and also the degree tax is also 1, it cancels out and it becomes 0, right? Okay. Okay, the definition sounds reasonable. It compares, like, it tries to show that the, let's say, real life world is a little bit much ordered and then like chaotic and randomness. And but the modularity has got some nice intuitive behaviors, but also has got some drawbacks and really counterintuitive behaviors. And what is nice about modularity? So isolated nodes, they do not matter, because as you think about the formula, it's all about the edges. And therefore, if we are talking about some asymptotic results on modularity, we refer most of the time, almost most of the time, to the number of edges, not to the number of vertices. Later, the nice thing is that also, if you come up with a partition such that you have a node of degree 1, which is alone in this community, it will always pay off to glue it together to the neighboring community, and it's gonna increase the modularity score of the partition. The other good thing is that if you have connected subgraphs in your graph, and you place, for example, 2 connected subgraphs together in the community, then if you look into partition that divides them into 2 separate communities, then it will not worsen your result. So it's also something good, something logical. But modularity also has some counterintuitive behaviors. And let me maybe mention just the 4th one listed over here, because this one is the most important from the practitioner's point of view. And this is called resolution limit. And one says that modularity suffers from resolution limit, or one says that modularity does not recognize small communities. Because what happens with this definition? So imagine that you've got a large network. And imagine that in this large network, you have like very small community, like very small cliques, let's say, very small cliques. And they're connected by an edge. So what will happen in the partition that optimizes the modularity score? If you have 2 very small communities in a huge large network, then if you look, well, so if you think about the random graph, it's going to be very unlikely that they are going to be connected by an edge, because they are very small. So expected number of edges between them will easily drop below 1. And then if our real life graph, this edge appears, it's a kind of a strong sign for modularity to glue them together in one community. So this is, for example, something that is a little bit annoying, this not recognizing small communities, as by naked eye, we really would like those guys to have in different communities like here, but the modularity will glue them together, right? All right, so modularity has got some drawbacks, but despite it, it's really like already well established and widely used. And even if you just look into clustering algorithms, and even if these are algorithms that are not based on this modularity approach, then modularity is often used, for example, as a quality function for those algorithms. So it's already like a well-established known parameter. All right, so these are some intuitions. How about some examples? So for complete graph, and this is a kind of a, if you ask people what do they think, like whether the complete graph has got community structure or not, actually people are divided. Some of them think that yes, the other think not at all. So modularity tells that no, that is 0, right? This is just by definition of modularity. The same for complete multipartite graphs. Star is just complete bipartite, so also. And if we take collection of R cliques, of course, we would like it to be pretty high, and it is. It is 1 - 1 over R. And this is a good moment maybe to mention the following fact, that if you have a partition which has got partition of the graph into K communities, then the modularity score of the partition cannot do better than 1 - 1 over K. And it's very easy to show. And if you have the partition into K communities, actually the best you can do, you have to have, so it is maximized, it is equal to 1 - 1 over K or 1 - 1 over R as here, if you put the same number of edges into each community. All right, how about structures like grids or hypercubes? Because these are very, very regular structures. And actually you don't spot any like, highly dense subparts in those graphs. You know, like judging by naked eye, we would like this modularity maybe not to be very high. But what turns out is that actually for such structures, the modularity is very close to 1 for grids and for hypercubes as well. For trees, there is some lower bound on modularity, which also, if the maximum degree of the tree is rather small, then also the modularity of a tree will be close to 1. So these are the examples of the families of graphs, which also maybe are a little bit counterintuitive with what we would like to expect. Maybe we would not like the grid or hypercube to have high modularity, as we don't treat those structures at having visible communities, you know, in their structure. So maybe it's good, and maybe it makes sense to just to research them, to be aware of the fact that high modularity not always indicate the presence of you know, like communities that we think when we just think loosely. Just also to have the example of the graph, which is with modularity not very close to 0 and not very close to 1, I can mention random cubic graph. And for now, it is known that more or less upper and lower bounds for modularity is like this. And it will also later appear in this presentation as some particular example. All right, so that's it about definition and some intuitions and some examples. Let me introduce the maximally modular class of graphs. So we say that the class of graph is maximally modular if whichever epsilon I choose, and I can always choose m epsilon such that if I look at the graphs with the number of edges bigger than m epsilon, I will be with modularity close to 1. I mean, modularity will be greater than 1 minus epsilon, right? So if I have a chance of talking about the sequence of graphs on m edges, then if the number of edges goes to infinity, the modularity tends to 1. This is the definition of the maximally modular class of graphs. We have already seen some examples, but let me recall trees, because we have seen that the lower bound for modularity depends on the maximum degree. So trees are maximally modular as long as the maximum degree in the tree is sublinear in the number of edges. This is what we get from this lower bound. Also, we have seen d-dimensional grids and d-dimensional hypercubes, and also so their degrees were constant, and also these were the families which were maximally modular. So here comes a natural question: whether we need this assumption for the maximum degree for a class to be maximally modular, and the answer is positive. So yes. So for maximally modular class of graphs, we have to demand that the maximum degree is sublinear number of edges. And it's very easy to show. So assume that we have such a graph that there exists one vertex of linear degree. So assume that we have a vertex of degree alpha m in G. And then just let's check what happens with the degree tags. Then, of course, whichever partition we take, this degree will have to belong to some community. And when it belongs to some particular community, it adds alpha m to the sum of its degrees. So degree tax will be always at least this constant. And if degree tax is always at least this constant, then modularity is bounded away from 1 by this constant. Right? All right, so it makes sense to ask the question, which classes of graphs with maximum degree sublinear in the number of edges are maximally modular? But this is very, very, very general question. And maybe it's worth to restrict the research just particular families of graphs. And since most of the graphs that we spot in complex networks are real life graphs, these are often, let's say, sparse graphs. Very often the number of connections is linear in the number of vertices. Therefore, it makes sense from the theoretical side to investigate some graphs which capture the notion of sparsity. So let's look in the family of nowhere dense graphs, and let's consider commonly considered subclasses of nowhere dense graphs. So the notion of nowhere dense graphs appeared in 2011, and it was introduced by Nechetril and Osona de Mendes as exactly something capturing the notion of sparsity of the graph. As the family of graphs, clipping together such structures on which problems that are normally algorithmically hard could become easy, could become computationally tractable. And before the notion of nowhere dense graphs appeared, people were thinking about maybe bounding degree or bounding tree width, but those concepts were not comparable. And when the definition of nowhere dense graphs appeared, it clipped together all the concepts that appeared earlier. So it's quite a robust definition. All right, so we asked this question. So we asked the question, which commonly considered subfamilies of nowhere dense graphs are maximally modular, but we of course additionally assume that the maximum degree is sublinear in number of edges. Otherwise, other families are not maximally modular. There have been some known results, and there was this nice theorem from 2020 by Colin McDiarmid and Fiona Skerman. And it tells that whenever we deal with a family of graphs or with a sequence of graphs such that the product of true width and maximum degree is sublinear in the number of edges, then modularity tends to 1. Then we have a maximally modular class of graphs. And to justify that the result is tight in a sense that the small o cannot be replaced by large O, they give two nice examples. So one example is a star. We have already seen a star together, and we have today, sorry, and we have seen that the modularity of star is equal to 0. And star is a graph which is a tree, so true width is equal to 1, but maximum degree is linear number of edges. So we have large O of M in the product of true width and maximum degree, and the modularity of the star is equal to 0. So this is one example of the fact that the result is tight. And now the other way around. So do we have something that has tree width linear in the number of edges and bounded degree? And here they state this random cubic example, which we already have seen also in the examples. So right now we have a graph that have tree width linear in the number of edges, bounded degree equal to 3, and modularity of such a graph was between 0.66 and 0.79. So, so this shows that the result is tight. And already this theorem resolves a part of our picture. So we always assume that maximum degree is sublinear number of edges. If we additionally bound tree width, then the product is sublinear number of edges and modularity tends to 1. So this lower part of the picture is resolved. All bounded true width graphs with not too large maximum degree are maximally modular, right? On the other hand, we have the example of the random cubic graph. And we have seen that its modularity is bounded away from 1 by a constant. So we have some bad example in the family of bounded degree graphs. So it means that this upper part of the picture consists of the subfamilies which are not maximally modular. But there is a part of the picture which contains exactly those 3 subfamilies. So planar, bounded genius, and graphs excluding a minor, which remained unsolved. And this is exactly the question that we wanted to answer. So consider those 3 families: planar, bounded genius, and graphs with an excluded minor. Assume that the maximum degree is sublinear number of edges, and try to answer the question whether these families are maximally modular or not, right? And we managed to prove that the family of graphs with an excluded minor is maximally modular. So at the same time, we have solved the question for bounded genius and planar graphs. Okay. All right, so this is the problem. This was the problem, and here comes the solution. I tried to sketch it briefly. So the first thing to observe is, all right, I have already mentioned this fact that if we have a partition of the graph into k communities, we cannot do better with the modularity score of the partition than 1 minus 1 over k. So it already gives a hint that if we want with our modularity to be arbitrarily close to 1, we have to be able to divide our graph into many small light components, but we cannot remove too many edges, because if we remove too many edges, then our edge contribution will drop and modularity will also drop. So if only we are able to take the graph and remove not many edges, and at the end come up to such a structure that consists of connected components such that the sum of degrees inside are not very big, we are done. So this general lemma is very easy to prove, and we're gonna do it. So what I want to do is I want to prove that if I remove epsilon half fraction of edges, and after removing those edges, I arrive at the connected components such that their volumes are at most epsilon half of the volume of the whole graph, then the modularity will be greater than 1 minus epsilon. This is the aim at the beginning. All right, so I'll just consider edge contribution and degree tax separately. And so I have removed epsilon half fraction of edges, so at most. So edge contribution is at least 1 minus epsilon half. So this bound is easy, but this is the lower bound for edge contribution. Now I'll make the upper bound for degree tax. It's also easy because each fraction. So at the end, I arrived at the connected components whose volume is at most epsilon half the volume of the whole graph. So this I use in this inequality. So altogether, I give the upper bound for the degree tax equal to epsilon half. So I have considered there a particular partition dictated by those small components gi that are left after removing epsilon half fraction of edges. So of course, modularity is at least as big as the modularity score dictated by this partition. So it's gonna be at least 1 minus epsilon, right? So if only I'm able to remove not like sublinear, let's say, number of edges and add up with the connected components whose volume are small, then I'm done. And I want to, so now the second task is to prove that if I take a graph, which is the graph with an excluded minor and not too large maximum degree, then I'm able to do such an operation, right? So I have to prove that indeed graphs with an excluded minor, they have such a structure that I can remove not many edges and arrive at the collection of connected components whose volumes are rather small. Right, so my task is the following, that I fix a minor, I fix epsilon, and I take G, which is H minor 3. I restrict its maximum degree by some delta times M. And my task will be to give delta as a function of epsilon, such that I will be able to remove not more than epsilon M edges and arrive at the graph composed of connected components whose volume will be at most epsilon, the volume of the whole graph. That's the task. That's the task. So it's just removing not many edges from H minor 3 graphs and arriving at the connected components with a very small volume. And the upper bound on maximum degree should help. All right. So in order to do that, we used a couple of tools. So the first one was Chigger's inequality. And Chigger's inequality gives some upper and lower bounds for the value called isoperimetric number or edge expansion. If you look at this expression, something is minimized over here. And what is minimized is the size of the edge cut divided by the minimum volume of the two parts that are remain after edges from the cut are removed. If we want to minimize such a ratio, it means that would like to find reasonably small edge cut, dividing the graph into maybe somehow balanced parts, right? Because this is going to be small if size of cut will be small, and also neither of those parts is going to be very small. If the graph has got a small isoperimetric number, it means that its structure that it's got a kind of a bottleneck. It means that there exists some small number of edges such that if you remove them, you're going to split the graph into still two big parts, right? And the Chigger's inequality gives some upper and lower bounds for this isoperimetric number in terms of the second smallest eigenvalue of the Laplacian of the graph, normalized Laplacian of the graph. But I'm going to just use the upper bound. So, and I'm going to rewrite this, this inequality a little bit. I just would like to upper bound the edge cut. So I'm going to rewrite it in the following way. And so by Chigger's inequality, I know that there exists some edge cut which I can upper bound by this expression. And I'm going to leave it here. Now I'm going to get rid of the second smallest eigenvalue of this normalized Laplacian by another nice result from 2010. The second eigenvalue of the graph Laplacian also tells something about the connectivity of the graph. It is called algebraic connectivity, and it tells how strongly the graph is connected, right? And there is a lizard by Bisval-Liu and Rao such that they managed to upper bound the second eigenvalue of the Laplacian of the graph in terms of the maximum degree and the number of vertices. And they did it for KH minus 3 graphs. So it's maybe it's a good hint if you would like to use Chigger's inequality, and we work with H minor 3 graphs, because first of all, if graph is H minor 3, then it's also KH minor 3, where the small h is the number of vertices in this big H minor. The second small, okay, so that's fine to use the theorem for KH minor 3 graphs. There is still a small inconsistency because Chigger's inequality tells about normalized Laplacian, and result by Bisval-Liu and Rao tells about Laplacian which is not normalized. But luckily, the inequality over here works the proper way around. So I can just, this part in the Chigger's inequality, replace by this upper bound, dependent on the maximum degree and the number of vertices from Bisval-Liu and Rao result. And this is what I'm gonna do. All right. The last thing that I'd like to change, I told you that that modularity is not sensitive at all to isolated vertices. They don't play any role for the value of modularity. So it's better to give some results and asymptotic results in terms of the number of edges, not the number of vertices. But it is known for graphs with an excluded minor that the number of edges is linear in the number of vertices. So I can just replace here the number of vertices by number of edges, maybe change the constant. And this way I arrive at a kind of a super tool that I'm gonna use to cut my graph. So now I know that if I take H minor 3 graph, then I'm always able to find an edge cut which is upper bounded by this expression. All right. And this I'm going to do in order to prove my crucial lemma, which generally speaking was telling that I'm able to remove not many number of edges to arrive at the number of small of connected components with the small volumes. All right. All right, so I'll just apply this tool iteratively. I'll just take my graph. I have fixed a minor h, I have fixed epsilon, and right, I have some h minor 3 graph. I cut my edge. What is the stopping condition? So when the connected component will be too small for further cuts, this will be the stopping condition. And over here, G prime appears when I say about the sum of degrees in the graph G prime, in the connected component G prime, because okay, whenever this appears as a subscript, it means that over here I think about the sum of degrees of vertices from G prime, but degrees of vertices with respect to G prime. And I cut the graph, I cut connected components as long as this inequality is true. So over here it's still true. So I make the cut dictated by my super tool. And I continue, at some point it will finish. And now the question is whether I have really removed at most this many number of edges, and whether really the volume of those connected components dropped below epsilon times the volume of the graph. And I'll try to convince you that yes, that it happened. And the next slide is a little bit technical, but I'll try to explain it like in a little bit more generality. So recall that the maximum degree is upper bounded by delta times m. And my task is to give you delta as a function of epsilon such that everything will be possible. So and let's consider just a single iteration on one connected component G prime. And so what I do, I apply my super tool, I make an edge cut. I have control over its size. I have the upper bound for its size. And let's just assume that by S, I will denote the smaller part of the graph that will remain after the edge cut. So by my super tool, I know that the size of this edge cut is at most this. And since maximum degree is delta times m, I can just rewrite it in this term, right? It is just a single iteration. It is just one cut on one connected component. And now I have to come up with some method for tracking over this whole procedure, how many edges I have removed in total. And what will be done over here is the following, that if I cut a connected component, then the vertices from the smaller part will be a kind of witnesses for the edges that were removed. So each vertex from the smaller part will remember some number of edges that were removed that belong to the cut. So each vertex from the small part will remember some number of edges that were removed. And each vertex will remember how many edges proportionally to its degree in the graph G prime. So if the total number of edges removed in this cut was this thing, then a single vertex V, which has degree V, will get assigned at most this number of edges. It is still just a single iteration. And now I have to, first of all, be conscious of the fact how many times such a vertex could get assigned edges. And later I have to sum it up over all vertices and the edges will be counted. If I do that, how many times the vertex could get assigned is also easy to calculate. Even if it always stays in the smaller part, it will not last forever. It can get assigned some edges at most this number of times because the procedure will stop as soon as the volume of this connected component will drop below epsilon half times the volume of the graph. If I sum it up over all vertices, I get what I wanted. I get that I have removed at most epsilon m number of edges, provided that delta was chosen properly, and I have cunningly changed the line, one line at the beginning. If you choose delta to be such small, then you get this inequality, and we are done. Okay, so by this procedure, by applying super tool iteratively, indeed I have removed not more than epsilon m edges. The second task to do was to ensure that the volume of each component was smaller than epsilon half times the volume of the graph. And it's already very easy. because the volume of each component is at most the sum of degrees in these connected components if I count them with respect to the graph, GI, to the connected component, plus at most the number of edges that were removed. For this, I have upper bound from my stopping condition. And for this one, I have upper bound which just have been calculated. So I really arrived at the small connected components with the volume not bigger than epsilon times the volume of the graph. So I got what I wanted. So just to recap a little bit. So the first observation was very general, that if I will be able to partition the graph into many parts with the many small volumes, I will have something of high modularity. And the second part was to show that indeed H-3 graphs with not too large maximum degree, they have such a structure. And this gave the answer to the solution. This proved that the class of graphs with an excluded minor is maximally modular, and automatically it resolves the question for bounded genus and planar graphs. Right. So this is the work that was done. And during the work, we have actually encountered one interesting thing, I guess, because we were searching a little bit about vertex and edge separators, because edge separator for H-3 graphs would help over here. And so how do we define vertex separators maybe first? So by vertex separator is a set of vertices in the graph such that if we remove this set of vertices, the graph is split into two parts, which are both still quite big. So, and very often it is defined like that both of the parts, they need to contain at most 2/3 of the number of vertices in the whole graph. Sometimes the definition of vertex separator is given also in terms of the weights. So vertices, they have assigned weights. And then we ask for those two parts that remain after splitting graphs to, so we demand that the weights of those parts are at most 2/3 of the weight of the whole graph. And analogously, we can define edge separator. So, but by edge separator, I understand the set of edges such that if I remove them, I split the graph into two parts, and each of the part, again, either its weight or the size or just the number of vertices, it has at most 2/3 of the number of vertices in the whole graph. And especially vertex separators are quite important also from practitioner's point of view, because if one, for example, approaches problem by divide and conquer method, one has to be able to find quickly, some number of vertices, some separator that would split the graph, and that they could approach the problem on the two parts of graph separately later and later glue the solution. So it was quite intensively studied. And so it is known that for planar graphs, vertex separator is of the order square root of n, and it is tight, it is best possible. So you can indicate, for example, grids that have indeed separators of this order. For vertex separator, it's also known for bounded genus and KH-3 graphs. And it turns out that it generalizes actually to the formula large O of square root genus times the number of vertices. We have also found the result for edge separators for planar and bounded genus graphs. And over here already the maximum degree appears. Because the vertices with maximum degree, they cause some problems for edge separators, but not for vertex separators, right? If you have vertices which have high degree, this is like the vertex which connects many things. If you are working with vertex separators, you can just get rid of such a vertex and the problem disappears. It's not the case when you need edge separator. So maximum degree appears here in the formulas, but we did not find the result for KH-3 graphs. And we also didn't come up with some super fast, easy argument that also this result could be generalized to KH-3 graphs, like it was done for vertex separators. And I thought that it's a very good place to ask whether you maybe know the result, or maybe you could come up with the solution, as this group is like strong in the structural graph theory. Maybe if you know well minor theory, maybe you could answer quickly. But so we haven't found the answer in the literature. And for some other open questions, let's go back to the modularity. So there are still a lot of gaps to close. There are still a lot of families of graphs to research. Even for very regular graphs, as you see, the direct answer is not known. And I think that especially interesting stuff would be to move on with the research in modularity towards the graphs that really mimic well these real life networks. So one of the first approach from 1999 was actually a so-called preferential attachment model. It was a dynamic model in which step-by-step vertices appear in the network, and when the network arrives, it is connected by k edges to existing nodes. But preferential attachment means that it will be always more likely to attach to vertices of higher degree than to vertices of lower degree. And for example, for this preferential attachment model given by Barabasi and Albert, the gap is really big because it's between some constant 15/16, which is more than 0.9, and 1 over square root of the number of edges added per step. And the conjecture is that the proper answer is in the lower bounds. All right, I think that's it. Thank you very much. I also like to show you maybe references and credit images, as some of them were done by me, but some of them were, or parts of them were taken from different sources. All right.
Thank you very much.
Thank you.